Kia ora koutou. Welcome to this video on ionic compounds properties. Just a reminder that we're currently going over Chemistry 2.4, which is demonstrate understanding of bonding, structure, properties, and energy changes. In the previous video, we looked at bonding and structure of ionic compounds. And so what I said in the previous video is that in the next video, we'll go over the properties of ionic compounds. So there's three or four different substances that we need to be able to look at the bonding, structure, and properties of, and ionic compounds is one of them. So we'll get straight into it. This could be a relatively long video. So what I'll do is either in the comments or on the screen, I'll let you navigate through yourselves to go to whichever property it is that you're wanting to revise at the moment. So don't feel like you have to watch this all in one go, but we'll go through it anyway. So ionic compounds properties. To get the outline of which properties we need to be looking at, we can go to the NZQA website. So we can go level 2 to structure and bonding. We get the standard here. So from this page, we can look at this is the achievement standard, like the outline of the achievement standard that we're going to look at now. Also, there are past exam papers. There are the resource booklets that we get during the exam. There's some exemplars that are put up. So these can be good to look at, but what I'd really recommend when you do practice exams is looking at the assessment schedule, which gives you what the suggested answer would be for each question. So right now we're just going to look at the achievement standard itself. From here, we can look down, and this is in your SciPad as well on the front page. So this gives us the scope of what can actually be examined in the exam. And so this is a part about properties. So properties are limited to hardness, malleability, ductility, electrical conductivity, melting and boiling points, and solubility. So these are what we're going to be looking at, the properties for ionic compounds in this video. So what I'll do is just take this and copy that onto our whiteboard. All right. So with ionic compounds, very common questions are about the malleability of ionic compounds. So that's their ability for a force to be applied and for the substance not to break. So we look at whether ionic compounds are malleable or not. Electrical conductivity is another very common question to be asked about them. Melting and boiling points, and also solubility. These, I would say, are the most common questions that you will get in terms of properties of ionic compounds. I haven't seen any questions about hardness or ductility of ionic compounds, but we'll have a quick look at how we might answer those. But we'll spend most of our time on malleability, electrical conductivity, melting and boiling points, and solubility. So when you're answering any of these questions on any of these properties, the way to start your answer is by describing the structure of ionic compounds. So we've gone over this a little bit in the last video, but we'll just do that just very quickly now. So I'm just going to pause the video and draw the 3D lattice that we would expect to see in ionic compounds. So this is the general structure. So it's a 3D lattice. Clearly haven't drawn it that well, but we've got alternating positive and negative ions held together by ionic bonds. So when answering any properties questions, you just want to start with a quick statement that describes the structure of an ionic compound. So we would say ionic compounds are made up of cations and anions arranged in a 3D lattice. So that is this. Clearly I've only done part of the 3D lattice, so this will go on and on a lot further. Arranged in a 3D lattice and held together by ionic bonds. So this statement, I just took this from the marking schedule, but that is a good statement describing the cations, anions, the bonds between them, and the overall structure. So any answer that you give for any of these properties, just start with a statement like that, and then we'll go on to describing how you would answer any questions about these properties. So to begin with, we'll go for malleability. So malleability is if you apply a force to something, is whether or not, if the force is large enough, whether the shape of the substance can change without the substance actually breaking. So you may or may not have tried this, but with ionic compounds, they are not malleable. So ionic compounds are brittle, which means that if you apply a strong enough force to them, then the bonds within the ionic compound will break and the substance will shatter. So ionic compounds are brittle. So we will just look into why that is. So if we take this structure here, so just for me to be able to describe it for you, I'm just going to draw this structure just as a 2D view and without the lines. So I'll just take a second to do that. Okay, so here it is. So this is a 2D version of this drawing here. So we're just looking side on, and I haven't drawn the lines to show ionic bonds in this case. It's just you've got the cation, anion, cation, anion, and then underneath you've got the opposite ion. So there's the forces between opposite ions there, which is why they're held together. So what we're going to do to describe what would happen with an ionic compound is we're going to apply a force to the ionic compound. And so let's say we apply a force just to this top layer. So that top layer is going to move across. So we're going to draw this again. Oops, I'll just do that while you're watching. So if we've got 4, so I'll do the bottom layer first. We've got 4 ions that I drew. And then what we've done is we've moved the top layer across 1. So we're going like this, 1, 2, 3, 4. So we'll draw these in now. So you can see the top one here, so we started positive, then a negative, then a positive, then a negative, and then underneath we had negative, positive, negative, positive. So can you see what's happened here? Normally with ionic compounds, they're held together because of that 3D lattice with the cations and anions arranged, they're alternating, and so there's the bond between the cation and anion there. When we apply a force and we shift a layer, we end up with these positive ions are aligned, these negative ions are aligned, and so because like charges repel, these 2 layers are going to shatter. So we've moved one layer, we've shifted a layer of ions, the ions are now lined up, like charges are now lined up, and so because like charges repel, the substance ends up shattering. So we'll have a look at a quick exam question. So for this one, we're going to I'll go back to the NCEA page. So have a look at the start of the video to work out how to get here, but basically I just Google NCEA standard 91164 if you wanted, or just NCEA level 2 structure and bonding. So you go to here. We'll have a look at the 2019 paper. 1B. So sodium is malleable. We'll look at that in a future video as to why sodium solid by itself is malleable, whereas sodium iodide is brittle. Explain these observations by referring to the structure and bonding of each substance. So we would need to do that. We don't have any space here for a diagram, so we're just going to need to describe using words why it is that this happens. So we'd need to say that if a force is applied to that sodium iodide, the layer of ions will move. This aligns like charges, and because like charges repel, the substance will shatter. So that was 2019 1B. We'll have a look at, if we were able to write that answer, we'll have a quick look at how we would have gone. So 2019, we can go down to marking schedule. So I'd highly recommend doing this when you're practicing writing exam questions, particularly for these word answers, is just to have a look at what they actually say in the model answer. So here we've got sodium iodide is made up of alternating positive ions and negative ions, ionically bonded in a 3D lattice. So that's the first sentence that we've used to describe the structure of sodium iodide, just like what we had done here. So that's just a more specific talking about sodium iodide. This is a generalized ionic compounds made up of cations and anions. So we start with that. We start with that statement there, just talking about the structure, and then we say sodium iodide is not malleable because if pressure is applied to an ionic lattice, it forces ions with the same charge next to each other, they repel each other and break the structure. So however it is that you would say that, if you comprehensively explain, this is how they would give you either an achieved, merit, or excellence based on that. So that is malleability. We will move on next to electrical conductivity. Sorry, I lied about that. We're not going to be doing electrical conductivity. I got about halfway through and then realized we should do solubility first. So we need to understand the principle of ionic compounds being soluble before we can fully be able to explain their electrical conductivity. So we'll do electrical conductivity maybe next, but for now we will do solubility. So not all ionic compounds are soluble, but we won't actually, in this topic, we kind of assume that they all are. You won't be asked about an ionic compound that is not soluble. It's always explaining the solubility of ionic compounds that are soluble. So how do we show that ionic compounds are soluble? So if you can imagine, salt is soluble. If you put salt in water, it will dissolve. So solubility describes a substance that dissolves in water. So we'll show this. I'll just draw a quick image of an ionic compound. So whoops, that should be a negative. It's a positive. So you've got an ionic compound with the ions like that. What we need to do to be able to describe that this is soluble is we need to look at a water molecule. And we need to look at the properties of a water molecule to help us explain why that sodium chloride, why is that piece of salt that you've put in the water, why is that able to dissolve in water? So water looks like it's H2O. So you've got an oxygen, you have two hydrogens. That's the H2 part of it. And you can watch, not that I've made it yet, but you can watch a video describing why this is the thing that I'm about to explain. But for now, you can just take my word for it. The oxygen in water, it's not like it doesn't have a full negative charge. It's not like chloride in salt, which has completely taken an electron. But with water, you've got this bond here, which is called a covalent bond, which means that electrons are being shared between hydrogen and oxygen. And what actually happens is that the electrons spend more time around the oxygen than they do around the hydrogen. And so because those electrons have a negative charge, we end up with this oxygen having a slightly negative charge overall. So this symbol here is delta. That describes slightly in this case. So slightly negative. So we're just drawing a molecule showing that there's actually a slightly negative part to it and a slightly positive part to it. One experiment that you can do to show this is that if you're able to get a plastic pen and rub it against your hair so that you get it kind of nice and static, you might remember doing little things like this, or a balloon even, little things like this in year 9 perhaps. So get some really good static charge and run a tap very lightly so that the water is just streaming out, and hold your pen or the balloon next to the water and see what happens. So when you see what happens, the reason for that happening is because this water molecule has a slightly positive end and a slightly negative end. So if your static electricity has slight positive parts to it, then the whole water molecule would be, if the hydrogen part of the water is closest to that statically charged object, then that would be repelled. So yeah, give it a go. Just run some water, statically charge an object, and hold it next to it and see what happens. So we've got water, this is called, when we've got a molecule that has these slightly negative and slightly positive parts to it, this is called a polar molecule. So water is an example of a polar molecule. So when we have salt, which is placed in water, what happens is that it's a similar concept to the positive and negative charges attracting. So you've got the attraction between opposite charges. So these positive charges of the water are going to be attracted to the negative parts of the salt, and then the oxygen is going to be attracted to the positive parts of the salt as well. So we end up, if this was a bit of salt that was placed in water, what would end up happening is that we would get positive ions, that this water molecule will interact with the positive part of the salt, surrounds it, and it pulls it away from the 3D lattice that it's in. So this ionic, or this cation, will end up being surrounded by water molecules. So you end up with these ions suspended in solution. So these are all water molecules there. And the same thing will happen with, so if that's a positive ion in this ionic compound, could be, for example, sodium when we're talking about salt. The same thing will happen with hydrogen being attracted to the negative ions within this ionic compound. So I'll just quickly pause the video and draw that as well. So so we have cations surrounded by the oxygen part of water, and anions will end up being surrounded by the hydrogen part of water. So we might get a question that needs to, often the questions about solubility of ionic compounds will require that we draw this diagram. So practice drawing the cation with oxygen atoms from water around it. We will then need to describe why something is soluble. So might say, describe why salt is soluble in water. Always just start with our description of the structure of an ionic compound. So if you were to get a question talking about the solubility of a compound, in fact, we'll just look at a past exam question. So there's one 2018. Go back a bit. 2018 examination paper. I just looked through these previously to find some example questions, but so you can do that at any time you want as well. So just when you see things, or no brain too small is really good, because it collates all of the past exam questions. So that's really easy to find past exam questions on a particular topic. So we have got, use an annotated diagram to show how solid A is able to dissolve in water. Show the solid before dissolving and the dissolving process of the solid. So we've pretty much done that. Well, we have done that here. We've shown this is it before being dissolved, and then we've shown that once it is dissolved in water, that's that part. And so we need to explain the attractions that allow solid A to be soluble in water. So we need to talk about the attractions between the hydrogen and the anion, and the oxygen and the cation within the compound. So we would say, first of all, start with your description of an ionic compound, and then say the oxygen, so slightly negative oxygen atoms, are attracted to the positive ions in sodium chloride, and then we'd say the negative, or the positive slightly positive hydrogen atoms. Notice I'm calling these atoms because when it's within water, it hasn't completely lost or gained an electron, so these are still atoms. So the slightly negative oxygen atoms are attracted to the positive ions in sodium chloride. The slightly positive hydrogen atoms are attracted to the negative ions in sodium chloride. So that's Cl minus. No, I can't do the superscript. Chloride, and then that would be sodium ions. These attractions are stronger than the attraction between ions within the ionic compound. So if you can imagine that if this negative and positive, if these ionic bonds were stronger than the forces that would between the hydrogen and the anion and the oxygen and the cation, then this ionic compound would just stay together. But these forces of attraction are greater than the forces of attraction within the ionic compound itself. And also between the water molecules. This is something that often gets written in an exam answer for this question. We'll have a look at it. My understanding of it is that there's forces of attraction between the negative parts of water and the positive parts of water as well. So there are forces of attraction between water molecules, which we'll go into later on in these videos. But so if you can imagine that if these forces of attraction between the water molecules were greater than the force of attraction between the hydrogen and the anion, then they would just stay together. They wouldn't be interested in this. That's my interpretation of it. But that's just what often gets written in the exam answers. So the slightly negative oxygen atoms are attracted to the positive ions in sodium chloride. The slightly positive hydrogen atoms are attracted to the negative ions in sodium chloride. These attractions are stronger than the attraction between the ions within the compound and also between the water molecules. And then we would just need to say, therefore, the sodium chloride ions are surrounded by water molecules. So NaCl is soluble. So we'll have a look back at that exam question that we were looking at. So explain the attractions that allow solid A to be soluble in water. I think in this case we're talking about sodium chloride, or it might not actually, it might just be a generic ionic compound. So this was 2018. So we'll go down to we'll get the assessment schedule for 2018. Here we go. So solid A is an ionic, and when it dissolves in water, it separates into its ions. The ions are charged and attracted to the charged ends of the polar water molecule. The slightly negative charges on the oxygen ends of the water are attracted to the positive ion, and the slightly positive hydrogen ends of the water molecules are attracted to the negative ion. So this causes the ions to be surrounded by water molecules and it dissolves. The solid is soluble because the force of attraction between the ions and water is strong enough to overcome the forces holding the ions together along with the forces holding the water molecules together. So that would be a model answer. So I probably haven't written as good an answer as that with this one. So maybe this wouldn't get you an excellence just by writing this, but somewhere along the way. So that's why you should always check your answers with the model answers there. So if you can get as close to that in practice as possible, then you'll be more likely to get an excellence. So if you drew a diagram showing the ions and water molecules, and that would be an achieved. So if you just did this part of it, that would be achieved. The diagram shows attraction between labeled ends of water and molecules and the ions in the diagram. That would be a merit. And then if you if you understand that, if you just have a statement that understands the strength of attractions, then that would be an excellence. So yeah, for this one, you might not actually need to write this full part of it. This is just a model answer. But so if you're showing that you understand that the strength of attraction needs to be stronger between the water and the ionic compound, then that would get you to an excellence. So that is a basic overview of the solubility of ionic compounds. So next, we will now get into electrical conductivity. So electrical conductivity, I told you this was going to be a long video. We're at 25 minutes already. And we're only partway through. So electrical conductivity. The electrical conductivity of a substance depends on the charged particles being free to move. So for a substance to conduct electricity, there needs to be charged particles. So charged particles can be either electrons or ions, free move throughout the substance. So we'll have a look at the structure of our ionic compound. So see how we've got the cations here, negative ions there. If you think of what's going on within the cation, there's been a reaction between the cation and the anion has completely donated an electron to the cation. Sorry, vice versa. The cation has completely donated an electron to the anion. So all the electrons in this cation are now really tightly held within that ion, and this one has completely accepted an electron. So that additional electron is held tightly within this structure as well. So the electrons are not free to move throughout this substance. The ions themselves, see how they're held together by those strong ionic bonds. So the ions are held in place and they're not able to move throughout the substance either. So when we're talking about ionic compounds as a solid, ionic compound solid, the ions are not free to move. So ionic compounds, when they're solid, do not conduct electricity. But we can find ionic compounds in different states. So for example, we could melt an ionic compound. So ionic compounds we'll find out have got high melting points, but they can be melted. So I'll just remind you of like the basic structure of like liquids and solids. So remember solids, if you were to put a solid in like a beaker, the particles there's strong forces of attraction between the particles. So the particles are not able to move past each other and they do not take up the whole space. So that's what we've seen with the ionic compound so far. So it's a solid. If you remember what the particles within a liquid look like, is that these forces of attraction are then weaker and the particles are free to move past each other. So when we've got when we have a liquid, the liquid takes up all available space within at the bottom of the container, and the particles are free to move past each other. So for an ionic compound, that will mean we've got the positive and negative ions, which are free to move past each other. Negative, let me see. Wouldn't look exactly like this. You don't ever get you wouldn't even need to show what the liquid looks like in a diagram, thankfully, because this hasn't helped. Um, oh, excuse me. So we would say that ionic compounds as a solid, as a liquid, have charged particles. These, in this case, ions that are free to move past each other, or free to move throughout the substance. So ionic compounds do conduct electricity as a liquid. Cool, so we've got ionic compounds as a solid where the ions are not free to move and so do not conduct electricity. As a liquid, the ions are free to move throughout the substance and so does conduct electricity. The final way that ions do conduct electricity, and the reason that I have talked about solubility first, is that when these cations and anions are dissolved in water, these ions are held within the solution and they're free to move throughout the solution. So if you've got an ionic compound in an aqueous form, aqueous, that is able to conduct electricity, the solution is able to conduct electricity because it does contain ions that are free to move. So yeah, those are the three states that we need to know about with electrical conductivity. So as a solid, ionic compounds do not conduct electricity. As a liquid, they do, and when they're aqueous, they do as well. We'll have a quick look at another exam question. So this one, we're on 2018. Yep. So if we look at 3B, 2018 3B. Here we go. So explain why solid A does not conduct electricity in the solid state, but will conduct when molten or when dissolved in water. So we'll work out how to find out which one of these solids are either molecules, ionic compounds, or metals, or covalent networks. But just for the moment, just take my word for it that solid A is an ionic compound. So we need to just use how we've described them here. First of all, we'll start by saying that there needs to be charged particles free to move throughout the substance for a substance to conduct electricity. And then we just describe within each substance whether or not there are those charged particles free to move. So we'll just have a look and see how we would go in terms of the marking schedule. So we'll go to 2018 assessment schedule, question 3B. So electrical conductivity requires a substance to have mobile charged particles. So we've just said particles, charged particles free to move. And then the general statement talking about the structure of an ionic compound in the solid state. So these ions are rigidly held in a lattice by strong ionic bonds, so cannot move around. When molten, the ions are able to move freely, so can conduct electricity. And then in an aqueous solution, the ions are also free to move, so the solution can also conduct electricity. So that's basically what we've said in this part of it. Yeah, we've talked about the charged particles needing to be free to move. What we haven't done in our answer here is describe the structure of an ionic compound in a solid form, but we just always need to make sure we do that. And then pretty much we've got the same answer. So we will now move on to what do we need? Melting and boiling points. So we'll look at melting and boiling points. So this is the fourth property that we're looking into. So melting and boiling points. So if we remember the difference between solids, liquids, and gases. So we've done a little bit here. So solids, they have got those strong forces of attraction holding the particles in place, so the particles can't move past each other. In a liquid, those forces of attractions have weakened, and so the particles are able to move, flow over each other. And then if we were thinking about a gas, let's draw that here. If you had like the particles there's no force of attraction between the particles, and so they're free to move throughout their container. So let's have a closed container there. So that's solid, liquid, and gases. What we need to do is talk about at which point, at which temperature, a substance will change from solid to liquid and from liquid to gas. So remember, solid to liquid, melting point; liquid to gas is the boiling point. So for water, for example, we know that if we were to heat water up to 100 degrees Celsius, that is the boiling point of water. So it goes from a liquid to a gas. The melting point of it is 0 degrees. So once we heat water up past 0 degrees, which it would normally be in our climate, it will melt and then turn to a liquid. So what happens with ionic compounds? So if you think if you imagine you've got your salt, as an example of an ionic compound, that is quite clearly solid at room temperature. So there must be something different going on between, if we were to compare an ionic compound and water, that means that ionic compounds are solid at a temperature that water would actually be a liquid. So what is it that determines the melting and boiling points of substances? It is actually the forces of attraction between these particles. So if there is a strong forces of attraction between the particles, then it would take a large amount of energy, of heat energy, for those particles to be moving fast enough for the bonds to be able to break. So the stronger the forces of attraction there, the greater the amount of heat energy that is required to break those bonds. So if we had a question about melting and boiling points, we would start by describing the structure of the ionic compound, and then we would just need to say that because the ionic forces, the ionic bonds holding particles in place in an ionic compound are strong, a large amount of heat energy is required to break the bonds. So ionic compounds have high melting and boiling points. Again, we'll just look at a past exam question. So we'll go to 2017 3B examination paper. So circle the substance that has the lowest melting point, referring to the attractive forces between the particles of all three substances. So we'll work out how to find out the melting, whether or not aluminium, magnesium chloride, or sulfur have high melting and boiling points. But in this answer, we need to describe, in terms of the structure of each of these substances, why do they have different melting and boiling points. So we'll have a look at the answer. 2017. B. So magnesium chloride is an ionic compound with strong ionic bonds between the cations and anions. These bonds also require a lot of energy to overcome, so the melting point is also higher than sulfur's melting point, or the melting point is high. So that one, it's not too much to write for the melting and boiling points of ionic compounds. So we've nearly made it through. So we've talked about malleability, electrical conductivity, melting and boiling points, and solubility. And so, like I was saying, I haven't really seen any exam questions about the hardness of ionic compounds or the ductility. But basically, for hardness, we would need to talk about the strength of ionic bonds. So we would always use this structure to start your answer. And then you would say that because these ionic bonds holding the particles together or holding the ions together is really strong, ionic compounds are very hard substances. And then ductility. Ductility is the ability for a substance to be drawn into a wire. So metals generally referred to as being ductile because they can be drawn into a wire. So if you've got a copper wire, the the copper can be drawn into a wire without it breaking. So I would say that you would use your answer for, if there was a ductility question that came up in an exam, would be similar to malleability. So you couldn't draw an ionic compound into a wire because it would involve placing a force on these layers of ions, and when the like charges align, the substance would break. So ionic compounds are not ductile and they are hard. So thank you for watching. Please like and subscribe for more great videos, more entertaining videos on Level 2 Chemistry. Look forward to the next video. Thanks.